going to make a simple truss. We're going to have a wall with a hinge on this side. And let's say that this is hinge A. And this hinge A is connected to hinge B by a bar. And then there is going to be another bar that connects hinge B to another pin, C, which is stuck to the wall. So pin at C, pin at A, two hinges, and a joint at B. And at this joint at B, I'm going to apply a load W. And I'm going to give you the geometry of this truss. Let's say that this is H, this is H, and this is L. And I'm giving you L equal to 4 meters. I'm giving you H equal to 3 meters. And I'm giving you the load, W equal to 7 kilonewtons. What I want the reaction at A, the reaction at C in X and Y, and I want the axial force in the two bars. So let's call the axial force inside bar AB NAB. And let's call the axial force inside bar BC, what do I call it? NBC, like the good TV station. OK. So I want to solve this truss. And let's say that I also take the time to give you the coordinate axes X and Y. If I hadn't given you coordinate axes, you choose coordinate axes. OK? But make your coordinates on the plot. OK, so this is our problem. Great, you say. I know how to do it. I've done this kind of stuff before, although it wasn't 2D. I just take away the support. Where I took away the support, I substitute with the reactions that the support were giving me. I put the structure in equilibrium. I find the reactions. Right? That's how we did it for 1D. So let's do a free body diagram of the whole structure. So the structure, once I free it, free from the support, looks like this. This is pin A. So Y is up that way. So remember, these are Cartesian components of the reaction. They go with the axis. RYA, RXA. At C, I have RXC, RYC. And remember the geometry is whatever it is. H, H, L. And actually, this one is a 3, 4, 5 triangles. And this angle here is 45 degrees. So in this case, I'm giving you a problem in which one of the two angles is defined by the length, so a 3, 4, 5 triangles. Some other types of problems, I may give you the angle directly, or somehow I give you the geometry of the way the bars are. Giving you the geometry of the way the bars are oriented is giving you the direction of the axial forces in the bar. Because remember, the axial force in each of the bar goes along the bars. So by giving you the geometry, I'm giving you information also on an important chunk of this problem, which is which way the forces are going. Okay? So let's do the sum of the forces X, sum of the forces Y, and sum of the forces Z. So I do sum of the forces X equal RXA plus RXC equal to 0. I do sum of the forces Y equal to RYA plus RYB. Now W, is it plus or minus W? On the Y equilibrium? Minus. Minus W equal to 0. I'm not done, because now I also have moments. So sum of the moment Z, and let's choose a pivot. Because these things are on the same line, if I choose the pivot at A in one clean sweep, I get rid of this, I get rid of this, and I can also rid of RxC, you see? So choosing a good pivot is very nice. So I do pivot with respect to A, and if I do the pivot with respect to A, I find that Ry is at distance L plus H, and it makes me rotate plus or minus? Plus, like that. So this is L plus H times RYC. Now, W is at distance L, right? And it makes me rotate plus or minus? Minus. So the moment of W with respect to A is simply going to be L times W. This is minus RxWy, by the way, right? So minus LW. Anything else?
Wait, you're saying W is the distance of L from point A?
Yes. So you can do this moment two ways. You can do it the thing of saying the arm of W, the line of W is a distance L from the pivot, and which way is pointing? That way. If I'm not comfortable with that, you can do it in the Cartesian way and say the moment Z is minus RxWy. And W, you know what I mean?
Like, isn't
I'm just messing you up.
Is W, we don't use like the hypotenuse or anything? We use just the X?
Well, imagine that you're doing the moments of W with respect to the pivot, right? So the moment, how much W makes you rotate is the force, but not, if it was pointing this way, I would have to take the whole distance. But it's pointing this way. So the only thing that matters is how far it is in the X direction. Review the forces and moment little video. If this is not clear to you, this is the moment to go back to look at the video on forces and moments, okay? Okay, but it's gonna take a little bit of working to get it all out. So I have three equations, 1, 2, and 3. Out of the third one, I see right away that Ry at C is simply equal to L divided by L plus H times W. From this equation here, I can get directly that, this should be C. Sorry about that. You guys should be more on top of my mistakes. What are you doing, slacking away? All right, so from this equation here, I see that Rya is equal to H divided by L plus H W, so that when I sum them together, I get L plus H over L plus H, which is 1, and together they give me W. And from this equation here, so this is good news. I already figured out this guy and this guy. Now from this equation here, I only get that Rxa is equal to minus Rxc. That's all what I get. You see? I don't know how much it is. Not enough information. Well, I do not just know that the whole structure must be in equilibrium. I know that every single chunk of it must be in equilibrium. So now I took the structure as a whole, but I can also take a part of the structure. So let's say that I want to use the fact that I know which way the forces in the bars are going. So let's cut through a bar. So let's take this part here of the structure. Simply that. I cut here, zip, 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 and I say this pin and this chunk of the bar must be in equilibrium. Okay, so let's take that thing. So this is my pin at C, so let's call it pin C. This is the bar. Let me just make a line for the bar. And I know that at pin C I have Rxc and I have Ryc. And I know that inside this bar, the only thing that can be there is an axial force, NBC. And I know which way it's pointing. It's pointing at 45 degrees from the horizontal because that's the way the bar is going. The geometry of the truss tells you which way the forces are pointing, tells you the direction of the force. Okay, so you say, well, that was very smart of you. Now you got another unknown. You had one extra, now you got another. And I say, yeah, but I got equations. I can say the sum of the forces x must be 0. So remember, your axis is always x and y. When you draw your free body diagram, draw your axis. Sum of x is equal to 0, that's Rxc. And then when I sum in the x direction, I need to take MBC times the cosine of this angle. So I have NBC cosine of 45 degrees. And it's plus or minus when I sum it in the x, minus. So when you do the sum x and sum y, look at your force and see which way they're pointing. If they're pointing against the axis, it's minus. And this one must be equal to 0. And the sum of the forces y equal to 0. That means that RYC, which is positive up, NBC sine 45 going down minus NBC sine 45 equal to 0. So I have these two new equations. That's nice, because I had only one extra known. So now I can figure out what things are. So from this equation here, because I know that RYC was this much, I get that NBC is equal to RYC, which is L divided by L plus H, divided by the sine of 45 degrees. So I have square root of 2. And that's my NBC.
Times W, wasn't it?
Oh, yes. Sorry. Absolutely. Because this one is just dimensionless, this factor here. So definitely there is something missing, times W. And I see that Rxc, when I flip this on the other side, I see that Rxc is also NBC cosine of 45. So if I multiply that by 45, I get L divided by L plus H. So what this tells you, if you think about it, it tells you that Rxc and Ryc must be equal so that they give me a force which is a 45 that can balance NBC. Makes sense physically, right? So that the pin is in equilibrium, right? So now I got everything, because Rxa is minus Rxc, so Rxa is equal to minus L divided by L plus HW. Okay, believe it or not, this is already a solution. So let's see if things make sense. I got the pins. So always check. After you find your solution, check it out. Check it. So your Rxa is minus L over L plus HW. So let's put the numbers in. L over L plus H is 4/7 of W. So that is 4 kilonewtons. Ryc is 3/7W, so that is 3 kilonewtons. This one is 7 kilonewtons. This thing here on the side is 4/7 times 7, so that is 4 kilonewtons. And the other one is also 4 kilonewtons. So that is what the structure looks like according to the calculations that I've done. This is the time in which you check to make sure you didn't make any mistakes. All of them came positive except this, so this I pointed the opposite way. See? Against Rx. Is the sum of the forces X 0? 4, 4, check. Is the sum of the forces Y 0? 3 plus 4, 7, 7, check. Does it make sense in terms of rotation? 7 times 4 and 7 times 4. Check. Okay, so after you're done your things, check your equilibrium and check if it's okay. Yes, it makes sense. Oh, we were asked also to find the axial force inside this bar. I can do the same trick I did there. I can do now pin A. On pin A, I have 3 kilonewtons coming up. I have 4 kilonewtons going that way. And I have a force here, and AB, which is on a 4, 3, 5 angle. Does it make sense? Absolutely. Because these together give me 5 that way. So that means that NAB is going to be equal to 5 kilonewtons.
What gives you 5?
What
gives you 5 that way?
Gives me 5 because if I take 3 this way and 4 this way, that are their X and their Y, this is a 3-4 triangle as well. So I know this force here is going to be 5. I can do things more carefully and projecting X and projecting Y, you find the same thing. Okay? So this came out as a bonus, right? By itself, we find that the last bar is in equilibrium. If you put the whole structures in equilibrium and everything except one last truss in equilibrium, that last truss is going to be in equilibrium by default. Because the whole thing is in equilibrium, everything around it is in equilibrium, that is going to be in equilibrium as well. Not only the bar is in equilibrium, but every single pin is in equilibrium. So if you look at the pins, think about the pins there. So let's do the pins. This is pin at A. Pin at A got RXA, RXA, RYA, and the force in AB. RXA positive coming up, 3 kilonewtons. Sorry, RY8 positive coming up, 3 kilonewtons. RXA negative, 4 kilonewtons. NAB positive, 5 kilonewtons. Angled on a 4, 3, 5 triangles. Does pin A look in equilibrium? Totally. How about pin B? Pin B has got 4 coming this way, it's got 4 coming this way, and it has got square root of 2 times 4 coming this way. All these are kilonewtons, not potatoes, not chocolate ice creams. Does that look in equilibrium to you? Absolutely. And finally, my loading on pin B, I got 7 coming down. I have 4 square root of 2 going up this way. I have 5 going up that way. The x component of this is 4. The x component of this is 4. 4 and 4 cancel out. They're in equilibrium. Oh, it looks like the Bruins. 4 and 4 cancel out. This one here comes up. This gives me 3. This gives me 4. 3 and 4 make 7, and we're good.
Now we'll see.
Oh, sorry. Yes. I lost track of who's what. Very good. Thank you. Okay? So if the whole thing is in equilibrium, the bars are in equilibrium, the pins are in equilibrium, we will be done. Except I still have a little bit of time. So what I want you to notice is that I did this and I said, okay, now we cut here, now we cut there. Sometimes it's not quite straightforward to figure out which one you take. If it's a complicated truss, what are you going to do? So I'm going to show you a nice method called the method of joints that actually uses this kind of concept of putting the joints in equilibrium to solve trusses in a nice step-by-step way that you do not need to think. You may be just, watching TV as you do these problems, because you just follow the path, and you just do it. So let's do the same truss here, get rid of all this stuff, and we're going to solve it using something called the method of joins.